Alright, so we're continuing our discussion on rational functions and their graphs. Let's recap these two common graphs. So here we have our reciprocal function, 1 over x, and we're going to create transformations with these parent graphs. So we talked about these before, and what we want to know from these parent graphs are the vertical asymptotes where they exist, and a couple of main points. So when I put a half, 1 over a half, I get 2, 1 over 2, I get a half, and then the same thing here except opposite signs. Remember, the difference here is we're squaring. Therefore, nothing's ever going to come out negative, so nothing exists on quadrants 3 or 4 unless I create some kind of transformation to this parent graph and shift this down or reflect it over the x-axis. So this is an odd function, this is an even function. This has origin symmetry, this has y-axis symmetry. When we input 1 into x, we get 1. When I input 2 into x, I get a quarter. And then when I input a half, I get 4. The same thing here, except our inputs are negative, our outputs are going to be identical, right? So here's an example of transformations, a sequence of transformations with rational functions. Let's take a look at this one. So this is where we're starting, and here's our parent graph. What transformation is occurring here? If I have 1 over x minus 2 quantity squared, what does this minus 2 do to the parent graph? Moves it to the right 2 units. Okay, so I should see the vertical asymptote move to the right 2 units, and that's exactly what I see. Notice that the shift to the right only affected the vertical asymptote. The horizontal asymptote is still here at 0. And then just move over the point that was at 1, 1, 1, 2 points to the right. The point that was here, 2 points to the right. Alright, now let's take a look at this one. What does this, not only are we moving this to the right 2, but what does this plus 1 up here do outside of my grouping symbols? It moves it up 1. So now we're affecting the horizontal and the vertical asymptote. Okay, so my horizontal asymptote moved up 1, right? And my vertical asymptote moved to the right 2. And these points, remember we started here at negative 1, 1, to the right 2, up 1. And then we started here to the right 2, up 1. And that's where these main points are coming from. Alright, so let's do our sequence of transformations for this parent graph. Let's just quickly create the graph of that parent that exists right here. And I know it's at 1, 1, negative 1, 1. So I'm just going to create a curve ever so lightly. And how is this graph moving? To the right 3 and down 4. To the right 3 is going to affect our vertical asymptote. So now it's at x equals 3. And down 4 is going to affect our vertical asymptote. So I'm going to go down 4 units. And the point that was at 1, 1, I'm also going to move it down 3 over 4. That's going to be right here. And my other one's going to be right here. And then I just create my curves. Let's do another one. Let's quickly reproduce the parent so that way it's just easier to graph. So remember, horizontal and vertical asymptote on the x and y axis, and this one has y-axis symmetry, and it looks like this. Okay, how is this graph moving? To the right 4 units, good, because this is in my grouping symbol. And what does this plus 2 do? Up 2. So to the right 4 is going to affect our vertical asymptote, and up 2 is going to affect our horizontal. And then just create your points. They exist here. Move them as well. To the right 4 and up 2. Alright, if we don't have the parent that we can transform, and I have a polynomial over another polynomial that's not fitting into that transformation model that I just showed you, it's a good idea to go through the strategy for graphing rational functions. First, we always want to determine what kind of symmetry does it have. Does it have y-axis symmetry, origin symmetry? Because that's going to help me determine, are my curves occurring like this? This is origin. Are my curves occurring like this? This is y-axis symmetry. Okay. Remember, your rational curves, they alternate. Okay. So you're having curves like this or curves like this. So we just need to figure out how are they alternating. Is it odd or is it even? The next thing we want to do is find intercepts. X-intercepts, God bless you. Y-intercepts. Find your vertical and horizontal asymptotes, and let's take a look at number 6. Plot at least one point between and beyond each x-intercept and vertical asymptote. So I want to figure out exactly what kind of behavior is happening between your vertical asymptotes and outside of them. And then graph. Let's take a look at it. Okay, so I said to begin by determining what kind of symmetry it is. So I'm going to pause, and I'm going to let you determine what kind of symmetry this has, and then we'll discuss it. Okay, that's right. This has origin symmetry. Okay, so we know it's going to have alternating behavior. So we figured out one, origin symmetry. If I put in a negative in for x and a negative in for y at the same time, the signs will reduce, and you end up with your given. So that's origin symmetry. The second thing we want to do is find our x and y intercepts. So I'm going to let x equals 0. I'm going to get y equals 0 over 0 minus 2. Your y-intercept is 0. Then the next thing I want to do is find my x-intercept. Let y equal 0. And notice that you're also going to get 0 here. So your x and y intercepts are 0, 0. All right. Now we want to find those asymptotes. Let's find our vertical asymptote. How do I find that? Whatever makes this undefined, so long as it doesn't reduce from the numerator, is a vertical asymptote. So x minus 2, nothing reduces it in the numerator. So x minus 2, set that equal to 0. X equals 2 is your one and only vertical asymptote. My horizontal asymptote, remember we want to look at the degree of the top in comparison to the degree of the bottom. They're the same. That means that you take your leading coefficient of the top, 5, and the leading coefficient over the bottom, which is 1. So y equals 5 over 1, or 5, is your horizontal asymptote. Okay. I personally like to start graphing at this point and then determine my other points in respect to what I have here. So let's start graphing what we have. I have a vertical asymptote at 2, a horizontal asymptote at 5. So let's graph that. So at 2, I'm going to create a straight line. And at 5, I have a horizontal asymptote. I have my one and only intercept, x-intercept, y-intercept is happening here at 0, 0. Okay. Remember, origin symmetry. What is this? What kind of behavior? Where must my curves occur? What I have graphed so far is enough information to finish off my rational curves. I know that nothing can exist on this piece right here. How do I know that? Because what did you say, Cedric? Okay, because I only have one x-intercept and it's here, and I'm not allowed to have any more x-intercepts here. Therefore, it must exist, your rational curve must exist up here, and you already have this point plotted, so you know that your next one is here. So what we could do at this point is create a table of values to help us be sure and determine what's happening on those portions of the graph. So I'm going to create a table of values. I'm going to substitute 3, 1, and -1 into the given. Alright, so these are the points that we get. And 315 is a little bit off our graph, but it helps us determine that we are on this top half. So somewhere over here is 315. And now I'm going to graph 1, -5. And I'm going to estimate -1 and 1 2/3. About right here. And now I'm just going to finish my curve. Alright, let's do another example. Let's first, remember, start by determining, is there any symmetry? This one has y-axis symmetry. I know that because if I put a negative in for x, it's not going to change this function. So it has y-axis symmetry, or it's an even function, whatever you want to call it. The second thing I want to do is determine my x and y intercepts. When I let x equal 0, I get 0 over negative 25, so your y-intercept is 0. When you set the equation equal to 0, you're also going to get 0 for your x-intercept. So your y-intercept and your x-intercept is 0, 0. Okay, so that's step 2 and 3 from our 7-step strategy. Now we want to determine where are our vertical asymptotes. Plus minus 5. It's whatever makes the denominator undefined so long as the numerator doesn't reduce it. So your vertical asymptotes, x equals 5 and x equals negative 5. What about your horizontal asymptotes? Good, it's 2. Because the degree of the top is equal to the degree of the bottom, you set the leading coefficient of the top over the bottom, so that's y equals 2. Again, I personally like to start graphing at this point. You can create your table of values if you want. So at 2, I have a horizontal asymptote. And at 5 and negative 5, I have vertical asymptotes. I already established that there is y-axis symmetry. Okay, we already established that there's y-axis symmetry, and I only have one point that's allowed to be on this x-axis. So that means I have to think back to those parent functions I talked about. I should have a parabola in here. And remember, you have always alternating behaviors happening here because you have y-axis symmetry. That means they're going to happen together. So if it's up here, it's also up here. I'm going to test that if I don't understand that concept using a table of values. So let's find what happens at 6, at negative 6, and let's substitute 2 and negative 2 and see what happens. So after we evaluate a couple points on our table of values, notice that we're consistently getting the same outputs, doesn't matter what we get. Here we're always going to output negative values because we need to be below the x-axis. We're never going to cross over for a couple reasons. One, we have a vertical asymptote that we're not allowed to cross over. And we don't have any more x-intercepts. So we must start dropping. And notice that the outputs are always going to be the same. At 1, we got 1/12, negative 1 over 12. I'm just estimating where these go. At negative 2, the fractions start just as small, and eventually you'll start picking up. And you will see that this behavior must be consistent. For 6, we outputted 72 over 11. That's somewhere up here. And the same behavior is going to occur over here. Because I have these asymptotes, according to the definition, I must approach it without bounds, right? And you see me drawing that. Let's talk about our slant asymptote. All right. Remember, when did we not have a horizontal asymptote? If the degree of the top was greater than the degree of the bottom. In that case, I could have a slant asymptote only if the degree of the top is 1 more degree than the bottom. If that's true, then when I do long division, this portion, not including the remainder, is my slant asymptote. And now I'm going to show you how to find that. So let's take a look at this example. Let's do long division to find our slant asymptote. Here we get x squared plus 6x plus 2. X squared divided by x is, multiply it out, take the difference, 0, bring down the 6x. 6x divided by x is, everything else is going to be a remainder. Do you guys agree? I'm not interested in the remainder. I don't care about it. All I'm interested in is this portion. That's my slant asymptote, and that's what I'm about to graph. So y equals x plus 6 is an asymptote that's slant. So let's call it SA, slant asymptote. Does this have a vertical asymptote? Yes, what is it? Good. Vertical asymptote is x equals 0. Remember, it's whatever makes this denominator undefined. All right. The next thing I want to do is find any intercepts, x-intercepts, y-intercepts. So I'm going to do that. Remember, y-intercept we find by letting x equal 0. When I do that, what do I get? All right, let's watch me substitute. Y-intercept, let x equal 0. So y equals 0 squared plus 6 times 0 plus 2 divided by 0. Okay, so anything divided by 0 is 0. So our y-intercept, not existent. Let's find our x-intercepts. When you complete the square, this is what you're going to end up with. X squared plus 6x, and that was plus 2. Remember, we're setting this equal to 0. Take half of 6, that's 3. Square that, that's 9. And now you want to subtract 9. We end up with 0 equals x plus 3, quantity squared minus 7. Bring the 7 over. Take the square root of both sides. So we're going to get x equals negative 3 plus minus the square root of 7. So we're going to say that x is approximately... Alright, and then we get these solutions, and now we actually want to start graphing what we have. So here, let's create a coordinate plane. And I'm going to start by graphing remember we have a vertical asymptote at x equals 0, so that's here. And now I want to graph my slant asymptote, which is y equals x plus 6. So my y-intercept for my slant asymptote is 6. And we're up 1 over 1. So here, I have a slant asymptote that exists right here. Alright, so our x-intercepts are happening at negative 5.64 and 0.35. So that looks like this, 2, 3, 4, 5. So we have a point that's about here and a point that's about here. How your slant curves occur are alternating behavior as well. And I know I must have a curve in here and a curve in here. Okay, for this example, let's just find the slant asymptote and make sure you guys got it. So what I'm going to do is long division. So we have x squared plus 2x plus 2. And in here, don't forget your place values. So this is plus 0x squared plus 0x minus 1. X cubed divided by x squared is, FOIL it out, x squared plus x cubed. X cubed plus 2x squared plus 2x. Take the difference. Here we get negative 2x squared. Here we get negative 2x. Bring down the 1. Negative 2x squared divided by x squared is negative 2. Multiply it out. We get negative 2x squared minus 4x minus 4. I'm not interested in the remainder. What I'm interested in is this. But let's find the remainder. Take the difference. Here we get 2x plus 3. So my slant asymptote is y equals x minus 2. And then from here, I want to find intercepts, graph my vertical asymptotes, which occur at wherever this is 0, but doesn't look like anything there. Okay, and then determine where your graph curves. Find the vertical asymptotes for the graph of the rational function. So which one of these are your vertical asymptotes for this problem? Okay, it's 4, right? So this is the only one that's there. It should be plus minus 4, but the only one that has the proper solution is B. Alright, what about this one? Find the horizontal asymptote for the graph of the rational function. A, it's y equals 4. Good. And last one, find the horizontal asymptote for this one. None, because the degree of the top is greater than the degree of the bottom.